There are 6 things that happens inside an LLM API call. Most engineers can name 2 of them. By end of the video, you will name all 6, and you will know which of those 6 you can test, log, and put a budget on. Hi, I'm Manoj Kumar, and this is MK Labs. And today we are in module 2 of the Get Started with AI for Quality Engineers in 2026 playlist. If you missed the module 1 on evals, the link is below. Check it out. Let's go. All right, inside the AI call. And this is very important because just like in testing, how important it is for you to know what the software does, how the architecture looks like. When you're fiddling with softwares and applications that are all built with AI, it is important to know what happens behind the AI call. And this is exactly this video is about. So once you know what happens behind the scenes of the API call, you'll better know what to test. And it'll also make more sense for you of all the eval-driven development that we spoke about. And so does the other videos in the channel. Yeah, let's go. All right, so here's a line I hear from QE folks all the time. It's just an API call. And honestly, you're right. You've probably made tens and thousands of them this year already. So look at the 2 panels. On the left, a plain REST API call, and the right you have a Python LLM client call. Imagine that's the client call LLM call that you're making into any models like GPT or Claude, Opus, and so on other models. On the right, an LLM call is in Python. A prompt, system message, response, latency, and retries. You can see all of those within. Same shape, right? The only thing that actually changed is the worker doing the job. It's not a browser on the other end anymore. It's a language model. Everything else you already know it. From a REST API call, you had request body, response body, and rate limits, whereas in the LLM client call, it's similar. The body is equal to prompt, and then you get the same response. And token coda is something that closely relatable as rate limits that you can. And everything else is something you already know, correct? If that API framing didn't quite land well for you, here's another example for someone who is in the automation space and someone who is fiddled with Selenium grid environments. Let's look at both, right? So on the left, I have the Selenium grid call. On the right, I have the LLM client call equivalent. So this is more or less on the Selenium 4 grid 4 architecture. Submitting a job, that's more or less like submitting a prompt. A worker node executing is a model node executing. A browser session is your context window. The capabilities object is your system prompt. Pay per minute becomes pay per token, and the failure modes you already fear. Rate limits, time modes, retries, they're all still here, right? The artifacts come back to you just as a response plus token counts. Same shape, different vocabulary. Pick whichever analogy sticks to your brain, and let's keep going. And this is going to get interesting, right? Right, so here's where it gets a little uncomfortable. Let's put your CI pipeline and your AI calls side by side. Your CI is fully instrumented, which is cost per build minute tracked, test execution time like P50, P95, P99, failed test costs classified, retry rates alarmed, quarterly spend sitting on a dashboard everyone looks at. So now your AI calls, if you look at it, it's almost similar, right? Cost per LLM call, token consumption is a huge question mark. Latency distribution, failure modes, quarterly spend, these are all a huge question mark across the board. Think about that for a second. Most of these cost real money. Both have real failure modes. Both have real failure modes, but only one of them is actually getting watched. That's the gap, and that's the whole point of today is to close it. By the end of this module, every one after the question becomes a number you own. So let's open the call up. From hi to the reply, 6 steps happen every single time behind the scenes of an LLM call. Step 1, your input, plain text, your prompt. Step 2, the text becomes token IDs at the scenes. Step 3, context assembly. Your system prompt, your user message gets stitched together. Step 4 is a forward pass. And notice I'm carefully not saying the model thinks. It doesn't. It computes next token probabilities, and that's all it's doing. If you've been following about the 30 Days of AI with Me series in YouTube Shorts, you'll better know that AI is a huge pattern matching engine. Go and check it out. And this is exactly what it's doing. It predicts the probabilities, and that's all it's doing. Step 5, sampling. Temperature picks one token out of that distribution. And step 6 is detokenize. It's written back into a text, and that's the reply you see. 6 steps, right? Here's the thing. Most engineers can name 2, maybe 3. By the end of this module, you'll name all 6 and tell me which are the ones that you can exactly test. Now, before we go deeper, I want you to actually see these six steps in moving, or perhaps a couple of steps that are very more important, right? So there is a website called, bebycroft.net/LLM. You can just open in the browser, and this is a live visualization of how an LLM happens, which can go deeper in multiple things like tokenization, sampling, and quite a few stuff. Okay, before showing the Bebycroft's website, here's what actually happens when you type a question into ChatGPT or Claude. 9 steps in 3 movements. You type an HTTPS post, a post call goes out, and the server builds you a full prompt. A system instructions plus conversation history plus your new question, all stitched together. And then the translation happens. Your text into integer IDs, embed those IDs into high dimensional vectors with positional encoding. So the model can do math on your words. Think of it as converting your plain text into zeros and ones and binaries. That's how your computers learn. And in this way, here is where the LLMs learn, right? The forward pass runs your vectors through the transformer stack. And the sampler picks one token from the resulting probability distribution. And here is what most tutorials skip, right? The steps 6 and 7 repeat once per output token. A 500 token reply means 500 forward passes. Latency scales with how much of the model says, not how much you asked. Finally, Detokenization back into text, package it as a response, envelope, and stream it back to your screen. 3 things worth remembering, right? Step 6 is nearly where 95% of the cost and latency live. And step 3 is the only window for new knowledge, which is why RAG exists. And the hot loop is the reason your build scales with output length and not input length. I hope that is really clear on what happens when you go and enter a question to what the model can. Now, to just understand a bit more, there are different websites where you can learn more about it. For example, if you type in, "Hi, how are you?" you can see the token count is 5, which is a base model. You can see how the numbers text comes into. For example, if you change this into GPT-5 Turbo, and the similar thing as a system, you're a helpful assistant, and say, I need help with my account. So imagine you're chatting with a chatbot, and this is what things happen, right? And these are the numbers that start getting back into a chatbot that reads through it. Now, similarly, transformers, right? There was a step in the transformers that comes through in here where, for example, what happens when you type a question to the LLM model and then it predicts, right? There are a couple of examples in here. So imagine the sentence, as the spaceship was approaching but the moment you do that, you can see how it happens from that input. So you can see at the front here, the transformer block 1, you can see as the spaceship was, it converts into these vectors, right? And you can come and see here the attention happens, then the output, right? So there could be multiple number of words, right? As the spaceship was approaching, it could be station or the surface or the planet, the end, the sun horizon. There will be a number of possibilities. You can see there are 0 probabilities of this word could match. But whereas this gives, a particular match so that it gives it here, right? And that is how it happens. And there are, 11 more identical transformers that you can look through it. So you can see how this comes through it. And this website is really, really in terms of understanding. If you want to know what happens behind the scenes, it says, "Welcome to the walkthrough of GPT LLM. Its goal is simple one. Take a sequence of 6 letters, C, B, A, B, B, and C, and sort them in alphabetical order, that is A, B, B, C, C." It's very simple from a human perspective. So what happens in the LLM world? So the moment you click on continue, you can see how the input starts and the tokenization happens. So when you click on the continue button, it just goes through one by one in the different steps. It's quite engaging and interactive once you want to do a really deep dive. If you're already doing and fiddling with LLM world, you know what K-weight, Q-weights mean. This is me just clicking on the continue button on the left hand side, doing nothing. But this is what really happens at the background. A lot of mathematical things happen. Hopefully this gave you some view around what happens behind the scenes, but let's go through our slide deck. All right, let's get back to the slide deck. Step 2 was tokenization, right? Let's go deep tokens for a minute because this is exactly where most engineers live. Tokens are not words. Look at these three strings. Customer can't log in. The customer cannot log in. Cust cannot log in, right? Customer can't log in about 5 tokens. The customer cannot log in about 6. And the third is also about 6 because CUST is an unusual prefix that splits into 2 tokens. Same meaning, 3 different costs. Now read the disclaimer at the bottom with me because it really matters. These counts as token dependent. Tick token for OpenAI. Anthropic uses a different tokenizer entirely. So don't trust my round numbers. Run your real strings through the real tokenizer before you optimize anything. Those websites that I showed earlier would really help you if you want to optimize the way how you want the LLMs to perceive this token. And yes, you can really tweak them. And here's a habit I want you to build, right? So count with tick token before you send. It's the same instinct that you would use a sanity check the size of your test data. Treat the token count like CI minutes and you'll never be surprised with the bill again. Step 3 was context assembly, and the container all that context goes into has a name, the context window. A short-lived memory, let's put it that way. The numbers you will hear thrown around are 8K, 128K, 1 million. But look at these bars at real scale, right? So 8K is about 6,000 words, barely a silver next to 1 million, right? So 128K is roughly a book chapter, and 1 million, that's a small code base. Now, a bigger window sounds free. It's not. Your cost climbs linearly with how much context you actually send. And that's a second sneakier problem, the lost in middle effect. Model pays strong attention to the start and the end of the context, and the middle quietly gets forgotten. And I'm sure most of you would have faced that. When you really have a long prompt, and sometimes may have missed some of the tasks, and carefully notice, go and check it out for yourself. It will be in the middle of the context. Now, here's a key rule that I want you to practice. Write it down, put your critical information at the top or at the bottom of your prompt. Never bury it in the middle because that's exactly where the model stops looking. Now, a little more about the context assembly because it's a big concept. So you've got 2 kinds of messages, the system message and the user message, right? And if you're a PyTest person, this maps perfectly. A system message is your fixture. You are a triage engineer. Return severity, component, reproducible steps. You set it once, it applies to every call. Stable preconditions, right? And the similar with JUnit and TestNG world, I'm sure most of you in automation will relate to that. You put the setup in the tear down methods, similar to that. The user message is your test input. Customer can't log in after 341 update. That's sent per call and it changes every time, right? And here is a discipline. It wouldn't mix your fixture and your test input in PyTest. So don't mix them here either. Factor the stable behavior into the system prompt the same way you would factor a stable setup into a fixture. Do that and 2 things get cleaner at once, your test code and your prompt. Step 5 was sampling and the dial that controls its temperature. Look at these 3 settings. If you're someone who is appearing for interviews on this QA with agentic skills, be very, very careful about the question on temperature. And if you never know how to answer the question with temperature, then you're not really into the AI world, and it's very important. At 0, the distribution collapses. The model picks the highest probability token almost every time. So setting temperature to 0 is very important. That's your home for evals, extraction, factual lookups. At 0.7, it widens. Creative but still coherent. Great for drafting and summarization. At 1.5, it flattens right out. Anything goes. And you rarely want this outside research. And now here's the part I really need you to internalize. Temperature equals 0 is the most repeatable setting you have. But it is not deterministic. Providers serving, tie breaking, model updates, they all sneak in with little variance for sure. So treat it like a low flake, not no flake. And here's a mind shift, right? This is the same skill you have used for 20 years, just inverted. For 2 decades, you fought flakiness. Now you're the one dialing it up, down for repeatability, same instinct, just opposite direct. I hope that really makes sense. So every single call has a meter, right? So let's see it run. Look at the code on the left. A real Anthropic API call with model and tokens. You have the system and the message with temperature is equal to 0, which we just talked about. Now look at the mirror on the right. Every response hands you back with input tokens, output tokens, and the cost as well as the latency. Sounds like nothing, right? But 10,000 calls a day, $84 a day. That's $30,000 a year for one feature. Right? So here's the line I want you to stuck in your head. The token is a new CI minute. You already know how to track CI minutes. Track these exactly the same way. And here's a slide most tutorials completely skip, and I want you to take as it's more important. Right? So the response from an AI LLM call is not just text, it's an envelope. On the left is the actual response object, content, stop, reason, input tokens, ID, model. All of that is what you assert on, what you log, what feeds your dashboard. But on the right is the field that matters most for testing. Stop, reason, 5 values, learn them. End turn means normal completion, green tick. You're good. Max token means your output got truncated. Your answer is literally cut off, and that needs an alarm. Look at stop sequence. Your custom stop string hit. Tool use means the model passed to call a tool. Your agent flow is waiting. And refusal means the model declined for safety reasons. That one needs an alarm too. But here's the takeaway. If you only ever check dot content and ignore stop reason, you will ship truncated answers and silent refusals straight to production. Please don't do that. 2 stop reasons deserve alarms, max tokens, and refusals. Wire them up. I hope this really makes sense, because when you do an LLM call, and if you really want to dig deep and see, it's just an object that comes back with all these parameters as a QLE pair, but all of them have a real meaning. If you want to test, you need to understand what happens. Now, for the QA leaders, right, it's a quick detour, and especially for the QA leaders who are in the chapter lead or leading the quality practice, watching this one, and this slide is exactly for you, right? This picture is a question landing in your next quarterly review. What's our cost per LLM call last quarter? If nobody in that room has a number, you don't have an answer, you have a story, not a good one. Look at the CI execution, 248,000 a quarter, tracked, alarmed, owned, build minute dashboards, P99 alarms, quarterly retros on cost. Now look at your LLM calls, question marks, right? Unknown, unknown, no cost dashboard, no latency SLOs, no quarterly review. Here's the good news. It's the exact same instinct that you built on your CI cost dashboard in the first place. It's just a new metric this time, same discipline. Go be the person who has the number. Now let's talk tools. What do you actually pick up on Monday, right? Here's the reassuring part. You already own most of them in the 5 rows, right? So look at Postman or Bruno, same tool. It works on LLM endpoints right out of the box. Your CI dashboards for cost and latency, bolt on Helico and Langsmith or Langfuse for LLM-specific observability and monitoring. Browser DevTools for inspecting runtime. The LLM equivalent for LLM is bycraft to actually see the forward pass. Your mental tokenizer for guessing input size. Replace it with tick token, the one that we saw earlier. In Python for exact count before you send. And distributed tracing, Zipkin Eiger today becomes Langsmith traces later. Giving you a per call execution traces. Notice the pattern. The instinct is identical what you've done before. The only thing that changes is the vocabulary here, as I've been telling this throughout the course. Now, this is the slide that ties the video 1 and 2 together. Stay with me, right? So back in previous video, we built a 4-layer evaluation cascade, schema, properties, model graded, and human samples. That cascade tested one thing, correctness. Now in this layer, 2 new layers are joined. So layer 5 is a cost budget. Same idea as that schema layer, cheap, deterministic, runs first, fails fast. Layer 6 is latency, same deal, right? And here's what makes it click. Both of these run right inside PyTest, and both fail. You build the exact same way, your regular assertion will fail. Snapshot, contract, cost budget, latency, you just drop them into a suite you already have. Same shape, same discipline, just a bigger surface area here. The same instinct that wrote your first 4 layers writes layers 5 and 6 as well. You're not learning a new craft here, you are extending the one you already mastered. All right, so what are you going to do next? And here is what I want you to do, right? So move 1, read every cost line, input tokens, output tokens, read them the same way you would read CI minutes for every bill. Move 2, move your stable behavior into the system prompt. Factor it exactly like you would factor a test fixture. Move 3. Use temperature 0 for anything you would want to green on read. Treat it like low flake, not no flake. Provided serving can still drift on you. Move 4. Cache aggressively wherever your inputs and model versions are stable. It's cacheable candidate, not a guaranteed identical result. But where it applies, it's a real win. And here's the thing, none of this is theoretical. All 4 on Monday morning code can ship you this week. Pick one and start there, right? And that's all I had in this video. Now that you can actually see the call, here's where we go next. We design the input that goes into it, right? So in next video, we tackle the AI test input, right? Because here's the reframe. Your prompts and your context windows aren't just text, they are your test inputs. So we are going to engineer them with the same care you would engineer test data. Read this spine line with me one more time. So read the spine line with me one more time. B1, B2, B3 are the videos 1, 2, and 3, right? So 1 and 2, 2 is this one was already there. You're going to look at it, right? So the first video taught you how to evaluate AI output, and the second video will taught you how to see the AI call producing it. And the third one, and that's important, will teach you how to design the input that goes in. 3 modules, 1 arc. So thanks for watching. Drop me a comment, which of these 6 steps did you not know about before today? I'll see you in the next video. Until then, take very good care of yourself. Thank you.